Hello and welcome to EDCI 349 lecture on chapter 11 in our elementary and middle school mathematics teaching developmental textbook. I am your lovely host, the great Dr. Brooks, and today we are talking about developing strategies for addition and subtraction. After this lecture and engaging in the activities embedded in this chapter, you should be able to identify the interplay between place value understanding and addition and subtraction computation strategies. You should be able to identify three types of computational strategies. You should be able to explain multiple invented strategies for addition and subtraction with multi-digit numbers. You should be able to explain the development of the standard algorithm for addition and subtraction, including ways to record students' thinking. Identify ways to teach computational estimation, to develop students' flexibility and ability to recognize reasonable answers, and describe computational estimation strategies for addition and subtraction. Much of the public sees computational skills as the hallmark of what it means to know mathematics at the elementary school level. Although that is far from the whole story, learning computational skills with whole numbers is in fact a critical component of the curriculum. Expectations for computation in today's workforce, as well as in daily life, mean that changes are warranted in how computation is taught. Rather than presenting a single method of adding or subtracting, the most appropriate method can and should change flexibly as the numbers and the context changes. In the spirit of Common Core and the Principles to Action, which is put out by the National Councils of Teachers of Mathematics, the goal is no longer just a matter of knowing how to subtract three-digit numbers. Rather, it is the development over time of an assortment of flexible skills and procedures that are meaningfully linked to conceptual understanding. So we talked about this in chapter 9. We want to present the students with a variety of strategies. We want to help them become extremely efficient in those strategies so that they will select a strategy that they are comfortable with, and that strategy might change depending on the various types of problems that the student encounters. More than just a means to produce answers, computation is increasingly seen as a window on the deep structure of the number system. Fortunately, research is demonstrating that both skilled performance and conceptual understanding are generated by the same kinds of activities. So we really have been more skills based. So we want students to be able to perform a skill, adding, subtracting, multiplying, dividing. But what we really need is for them to have a conceptual understanding. Why are you adding? Why are you subtracting? Why are you dividing? Those two skills, the skilled performance and the conceptual understanding, can both be learned from the same activities. Unfortunately, in the past, we have focused on skill development and not on conceptual understanding. Why are we performing this skill? That takes longer to teach to a student, because it involves allowing them to talk to us about how they arrived at their answer. And a lot of times students have a hard time articulating how they arrived at an answer, and we as classroom teachers have a hard time allowing the students to articulate their answers. So we want to make sure that we teach our we teach strategies that allow for students to have a conceptual understanding of this standard algorithm. Why do we add? Why are we subtracting for this problem? And when you ask students to give you an answer and then explain their answer, they normally can give you an answer, but it's a challenge for them to explain how they got their answer. Each chapter has some big ideas. What are you going to be your big takeaways from the chapter? From this chapter, we want to be able to allow, we as the teacher want to develop students who are able to use flexible methods of addition and subtraction. And that involves taking apart a number, which is, we learned in the last video, down under 10, combining, building 10, inventive strategies. So an inventive strategy is just what it sounds like. The students actually come up with their own way to solve the problem. And we'll talk more about that later, because even though it's invented, that the students invented, they're normally going to come up with one of 4 different ways of inventing. We want them to be able to decompose numbers based on place value or compatible numbers. And that's why we have them build 10s, or remember 5 as a foundation. Building flexibility comes from students having a deep understanding of the concept. They can have, for math or adding and subtracting, that's having a deep understanding of the commutative and the associative properties. We want also to teach students how to decompose and compose multiple digit numbers. We also want them to understand the standard algorithm, but we also want them to use some estimation to handle parts of a number. And we want students who think about what the answer could be, so that when they come up with an answer, it is close to what they've guessed. And that's another skill that we in the classroom have to make sure that we work on. Because we're not asking students, because of time, we're not asking students to work on to estimate what should the answer be. What do you think the answer is? Okay, now let's solve it. Was that close to your guess? Or when they come up with an estimate, have them explain, why did you guess that estimate? Addition and subtraction strategies that build on decomposing and composing numbers in flexible ways contribute to students' overall number sense. In most everyday instances, these alternative strategies for computing are easier and faster than standard algorithms. When we teach students how to break it apart, or combine it, build 10s, foundational 5s. Remember, in our last chapter 9, we talked about 2s, 5s, 10s, 0s, and 1s. When we help students learn how to use these strategies, it helps them to be able to do mental math and do math better. They offer a problem on page 239. Mary has 114 spaces in her photo album. So far, she has placed 89 photos in the album. How many more photos can she put in it before it is full? So here goes a situation where there are multiple ways to solve this problem. We, as the classroom teacher, automatically want to apply the algorithm 14 minus 86 equals. But the algorithm comes last. And we'll talk about that during the chapter. First, we will want to present, and remember, we don't want to give naked numbers. I love that. We don't say that often anymore. We don't want to give naked numbers. We want to embed problems in real life context. And then we want to just step back. We want to present the problem. We want to step back after we've provided all of these strategies, and we want to let the students attack the problem. And then we want to come in and offer supports to the students. Computational fluency. Computational fluency means that I can select a variety of methods and strategies to attack a problem. Computational fluency is something that we as the math teacher will have to teach our students. And in order for them to be fluent, we have to give them a lot. We have to help them have a deep understanding of the strategies, because that's how they will build fluency. Connecting addition and subtraction to place value. Research suggests that problems involving addition and subtraction are a good context for learning place value. If students only understand computation as a digit by digit exercise and not the value of the numbers involved, they make many errors and are often unable to judge the reasonableness of their answers. Let's say that again. If students only understand computation as a digit by digit exercise and they don't know the value of the numbers that are involved in that digit by digit exercise, they make errors and they often cannot judge the reasonableness of their answer. So if we just teach students 3 plus 4 is 7, later on when we move to multiple digit numbers, students can have a problem. So we need to be teaching that it's 3 ones plus 7 ones equals this new thing called a 10. We need to get back to basics and helping students become familiar. And we need to make sure that we use the language and the terms that they use in math. Compatible numbers for addition and subtraction are numbers that easily combine to equal benchmark numbers. Numbers that equal tens or hundreds are the most common example. Benchmark numbers are, 5, 10s, those are your benchmark numbers, and then iterations of those 15, 20, 25, 50, 75, 100. Those are your benchmark numbers. We want to make sure that we're talking about compatible numbers. And we do this when we break things down and we build 10. Again, video 9, the whole video was talking about different strategies. And one of those strategies was or several of those strategies relied on these compatible numbers, building 10s, building 5s, because those are numbers that we teach skip counting. And we teach skip counting very early in a student's career. And so if we can take a skill that they already have and we can build upon that. So there are a lot of activities in chapter 11 that talk about taking away subtraction using models. We should make sure that we use models, 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 when we're teaching addition. And we'll talk more about that. I think in the lecture we mentioned using more and more models. Model, model, model. All right, there are 3 types of computational strategies. Computational strategies. Computation just means computing, finding the answer, whether it's addition problem, subtraction, multiplication, or division. So there are 3 types of computational strategies: computing strategies, solving strategies. There is direct modeling, where I have 3 items. Let me get my handy dandy. One, 2, 3, 4, 5 equals 5. And we would model this, so we would use manipulatives. I've got manipulatives. 1, 2, 3. 1, 2, 3 fruit plus 2 toys equals 5 items. 1, 2, 3, 4, 5, 5 items in all. You'd want to teach that concretely using models. Then we have, so direct modeling is just that. I'm going to use models to display the computation that I want students to perform. Doing the modeling, building tens, breaking apart tens, can help students understand the importance of building 10. And it can also help you when you're doing modeling and building tens and breaking apart tens. It can also help you see where a student's misconceptions or misunderstandings lie. The next is the invented strategies. An invented strategy refers to any strategy other than the standard algorithm, or that does not involve the use of physical materials or counting by ones. For first and second grade, the Common Core Standard describes these strategies as based on place value, properties of operation, and or the relationship between addition and subtraction. More specifically, students are expected to develop, discuss, and use efficient, accurate, and generalizable methods to compare sums and differences of whole numbers in base 10 notation using their understanding of place value and the properties of operation, commutative and associative in the case of addition and subtraction. At times, invented strategies become mental methods after the ideas have been explored, used, and understood. For example, after some experience, students may be able to do 75 plus 19 mentally. So let's look at that. 75 plus 19 mentally. They can do, some students might say, look at it and say, remember, this is inventive. So you've presented this problem, and I can think of 2 ways to solve this problem, invented. I can say, well, I know that 3/4 plus 1/4 gives me $1, but I have 6 pennies less. So if I count backwards from 106, from 100, and I count backwards 6 spots, I get 94. Or I can say 75 plus 20. So I can count by tens, 75, 85, 95, minus 1, because of the 19, gives me 94. So there goes 2 invented strategies that students can use to solve the problem. Contrast with standard algorithms. Consider the following significant differences between an invented strategy and an algorithm, the standard algorithm. Invented strategies are number-oriented rather than digit-oriented. That's a big one. Number versus strategy. Number versus digit. Make sure that you are using this language with your students. How many digits are in our base 10 system? How many digits are there? That's going to be a quiz question. How many digits? Versus how many numbers? We need students to understand that there are only 10 digits, and those digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. There are infinite numbers. We don't know all the numbers. When I was young, if a million was a lot. Now we have a trillion, we have a billion, we have a lot of numbers. I would say zillion, but I'm not sure about that one. Invented strategies are left-handed rather than right-handed. What does that mean? Inventive strategies often begin with the largest parts of numbers, so it starts at the left, because they focus on the entire number. For the problem 263 plus 126, many inventive strategies would begin with 200. So the problem 261 plus 126, under the inventive strategy, they might start with 100 plus 200 and then move to tens and then move to the ones. So it can start at the left and not at the right. Inventive strategies are a range of flexible options rather than one right way. Inventive strategies are dependent on the numbers involved so that students can make the computation easier. And so inventive strategies are going to vary based on the student and based on their ability levels, their comfort level, and their understanding. The more a student understands about computations, about numbers, about digits, then he will use a different set of invented strategies. But we don't want to talk about the algorithm until we first spent time letting them decide how to come up with an answer, and remembering that there is not one right answer. Benefits from did I skip one? No, I didn't. All right. Benefits of an invented strategy. The development and use of invented strategies generate procedural proficiencies and more. Procedural proficiencies. So once students develop and use inventive strategies, that is going to help them be able to do the algorithm. That's what that is, procedural proficiency. That means that once they're using inventive strategies, then they'll be able to apply the algorithms. Standards. Students make fewer errors. According to the research, students who use inventive strategies make fewer errors than students who just use a traditional algorithm. And that's because with the algorithm, there really is no checks and balances. If I put 3 plus 4 is 8, until the teacher puts that red mark on my paper, I don't know that the answer is wrong. Whereas if I use an inventive strategy, I drew a picture, I used a counter, I built tens, now I might be able to see the flaw in my thinking. Less reteaching is required. When students are able to attack a problem in the manner that they're comfortable and strong in, they're more confident in it, they're able to come up with the right answer more often, and less reteaching is required. Students develop number sense. Students develop and use the use of number-oriented, flexible algorithms offers them a rich understanding of the number system. Students who have an understanding of numbers because they've used inventive strategies are able to do math better than students who don't. They can do math better using inventive strategies than students who only use the traditional algorithm. Inventive strategies are the basis for mental computation and estimation. When inventive strategies are the norm for computation, there is no need to talk about mental computation as if it is a separate skill. Mental computation and inventive strategies work together. As students become more proficient with these flexible methods, they find they are able to use them mentally or sometimes only need to jot down intermediate steps. So as students use their own inventive strategies, they are more comfortable and confident, and it helps with the mental computation and estimation. And we want them to be estimating the right answer so that when they come up with the answer, is it close to their estimate? But we want them to be making these estimations based off of research, based off of a strategy that they've used, not just some number that they've grabbed out of the air. And I feel like in the past, that's how estimation was taught. It was kind of like just pull a number or any number. But that's not what estimation is. Estimation is based on these strategies, based on a set of circumstances. This is likely going to be the answer. And this is why it's likely to be the answer. And then when I solve my problem, then going back and looking, is it close? If it's not close, where is the discrepancy? Why did I have a problem? We need to spend a lot more time in the math class talking about math and less time doing the algorithms in math. Flexible methods are often faster than standard algorithms. We talked about that for chapter 10. We've talked about chapter 9. Talked about that in the past. Building tens and building fives and using doubles or near doubles. Those are just easier. They're faster for students. And then again, they'll get more accurate answers. Algorithm invention is itself a significantly important process of doing math. So the students do need to learn how to do algorithms, but that's not what you start with. Inventive strategies serve students well on standardized tests. Inventive strategies, and again, we'll talk about that, there ends up only being 4 types of inventive strategies. You can't teach students everything they need to know. What you can teach and what you are to be teaching is for students to be able to figure out the answers to different things, especially when it comes to standardized tests. So when students are using inventive strategies, they can then they're able to take strategies that they've developed themselves and apply that to all different types of situations. Mental computation. A mental computation strategy is simply any invented strategy that is done mentally. So a student, and remember, inventive strategy isn't just the student just comes up with a way to solve the problem and the student writes it down. In order for it to be a strategy, the student has to tell you what was their thought process? How did they move from the problem to the answer? And then they need to be able to apply that time and time again. Then we have the standard algorithm. There are 3 main components in the trajectory of learning about standard algorithms. First, knowing the step-by-step process and how it is performed. Second, knowing why the algorithm works and how it can be applied. And third, knowing when an algorithm should be used and comparing the value and usefulness of different algorithms. The Common Core require that students eventually have knowledge of standard algorithms, addition and subtraction with multiple digit whole numbers in grade 4, multiplication with multiple digit whole numbers in grade 5, and division of multiple digit whole numbers in grade 6. Notice that the grades in which this knowledge of standard algorithms is required is long after the time when the topic is introduced. So this is talking about 4, 5, and 6, but chapter 9, we already learned that we are teaching addition, subtraction, multiplication, and division starting addition, subtraction in kindergarten, the multiplication and division second grade. But we're not introducing the algorithm until 4th, 5th, and 6th grade. Because during the early years, we're helping them to develop strategies. And if remember in chapter 9, we looked at a bunch of different reasoning strategies. If we give students that in kindergarten, first, second grade, and we give them these reasoning strategies, that is the basis for them to build their inventive strategies. First off, standard algorithms must be understood. The student must understand why this works in this situation. Students may learn the standard algorithm from siblings or other family members while you are still trying to teach a variety of inventive strategies. Some of these students may resist learning more flexible strategies, thinking that they know the right way. What do you do then? First and foremost, apply the same rule to standard algorithms as to all strategies. If you use it, you must understand why it works and be able to explain it. And a lot of times, if you give 3 plus 4, just the standard algorithm, and you ask students, why does this equal 7? Tell me, they won't be able to. Whereas with an inventive strategy, I had 3 apples. Susan gave me 4 more apples. How many apples do I have? The student says, well, I had something. Somebody gave me some more of something. I ended up with more than I started with. That's why I need to add. But that doesn't happen overnight. That happens with a lot of practice, problems, word problems, and a lot of reasoning skills. Page 250 says, delay, delay, delay. You want to teach or implement the standard algorithm later in the curriculum, not earlier. So you don't want to start with 3 plus 4 in kindergarten. You want to always embed the problem. And here's the problem. Oh, look, I have everything. Teacher Shonda has 2 green apples. Teacher Sarah has 4 green apples. How many apples do they have altogether? How many apples are there? I want to give models, and I'm teaching addition long before I ever teach this. Remember that. I want to model, and I want to delay the implementation of standard algorithm until after the students understand the various strategies. And I also want to understand cultural differences in algorithms. Some people falsely assume that mathematics is universal and is easier than other subjects for students who are not native English speakers. In fact, there are many international differences in notation, convention, and algorithms. Knowing more about the diverse algorithms students might bring to the classroom and their ways of recording symbols for doing mathematics will assist you in supporting students and responding to their families. What the United States calls the standard algorithm may not be customary in other countries, so encourage a variety of algorithms is important in valuing the experiences of each and every student. For example, equal addition is a subtraction algorithm used in many Latin and European countries. It is based on the knowledge that adding the same amount to both the medium and the subtrahend will not change the difference, the answer. Cultural differences should not just be in the forefront of your mind for math. Cultural differences should permeate your whole teaching strategy. So you need to understand that students come to you from different cultures, and based on those cultures, they have different expectations, different behaviors. But especially if they come from a culture that it originates outside of the United States. Sometimes even the convention of reading is different. We read left to right, top to bottom, but that's not all countries. Some countries start at the bottom and read to the top. Some countries do right to left. And so making sure that you are aware of cultural differences is important. All right, this has hit the 30-minute mark. I'm going to pause, let you walk and get some water, let you go see about the kids. When we get back, we will be on page 251, Development of Inventive Strategies in Addition and Subtraction.